All right, so we did the first problem together. Um, so this one, I'm thinking, okay, are there any zero slopes? Well, that'd be when y equals zero, right? So y equals zero here, so zero slopes. Put all those on there, which also might kind of show some symmetry. Is it ever undefined? Nope. Really just depends on y. So it doesn't matter what x is. If y is 1, the slope is 2. Up 2 over 1, up 2 over 1, up 2 over 1. And I'm always using these other dots to kind of line it up. If you plug 2 in, you get a slope of 4. It's up 4 over 1, 4 over 1. So you really can crank these out, and there's probably symmetry down here. If you plug negative 1 in, it's negative 2. Now I'm lining up these squares down 2 over 1. Down 2 over 1. Plug in negative 2, you get negative 4. So, you can find patterns. It can be quick. Now, what kind of graph does this look like? It has a horizontal asymptote at y equals 0, and then it gets bigger and bigger and bigger as it gets further away. I mean, it kind of looks exponential. So we separated the variables yesterday. So let's finish solving. Got to exponentiate both sides, right? And that would give you absolute value of y equals e to the 2x plus c. And then you could get rid of the absolute value by doing plus or minus. Now, rules of exponents say that you could break this apart like that, and e to the c is just some new constant, which I'll just put out in front. And this is your solution. That's your general solution. So it's kind of weird that the c value doesn't actually result in a shift, which the slope field shows there isn't a shift. It's more of like the c just makes it steeper or less steep. They all have the same horizontal asymptote, no matter what the c value is. So that's your general solution. The plus or minus would get sorted out when you found the c value with an initial condition. So it'd either be the upper one or it'd be the lower one, the upside down version. Okay, this one here, does it equal 0 anywhere? Well, where these equal 0, y equals negative x, that's this line right here, right? All along that line, actually, no, not that line, this line right here. All along that line, you have 0 slopes. So sometimes it gives you the equation of where those are. Is it ever equal to undefined? Division by 0? Nope. Okay. There might be some kind of symmetry. There might not. We can just start plugging values in. And the fact that all these values are along this line, I bet there might be similarities along these other sort of downward diagonal lines. So if you plug 0, 1 in, 0 for x, 1 for y, you get a slope of 1. If you plug, let's try this one, negative 1, 2, get a slope of 1 also. So I think all of these have a slope of 1. And then these probably are all going to be same. If you do 0, 2, you get a slope of 2. If you do 1, 1, you get a slope of 2. So these are all going to be slopes of 2. All right. And then 1, 2, those are all going to be slopes of 3. So a little steeper. And 2, 2 is going to be slopes of 4. It's going to be even a little steeper. It's going to be kind of, and 3, 2 is going to be slope of 5. So probably along here, these are going to be the same, but maybe not symmetric. This one's kind of a unique problem. Negative 1, 0 is going to have a slope of negative 1. And 0, negative 1 is going to have a slope of negative 1. So these are all probably negative 1. Now, the interesting thing of here is if you ever have slopes going directly into each other and they just stay on it, that's an asymptote. So this is a slant asymptote, which some rational functions have that. Some functions have slant asymptotes instead of horizontal and vertical asymptotes. Okay, -2 would be a slope of -2. -1, -1, slope of -2. So these are all -2. -3 is a slope of -3. -2, -2 is a slope of -4. So we are getting some similar kinds of slopes as over here, but I don't know, it doesn't look super symmetric. -3, -1, slope of -4, and then -5, a little steeper. So that's your slope field. The interesting thing is if you get initial condition up here, it'll go like that towards, I could just sketch it. It's going to go kind of like it's going to go towards this slant asymptote like that. That'd be a solution. If you picked one over here, it'd have kind of a totally different shape. Look like that. If you got one on this line, the solution would actually just be a straight line. So it depends on the initial condition, the shape of the graph. We can separate the variables here. You just can't do it. It only can involve multiplication or division to get the x's and y's and dy's, dx's. That plus right there is going to cause problems. Okay, number 4. I'd look for 0 slopes first, which is going to be when x equals 0. So that's the y-axis. They're never undefined, but this might provide symmetry. It just depends on x. So when x is 1, you get a slope of 2, no matter what the y value is. When x is -1, you get a slope of -2, no matter what the y value is. When x is 2, you get a slope of 4. -4. 3, it's slope of 6, so it's even steeper. So, I mean, they kind of look like parabolas, maybe, kind of, kind of looks like that graph. So let's see if we can solve it. Let's separate the variables. This one's actually pretty easy to separate because there are no y's. So you just move the dx to the right side. We integrate both sides. 2x squared over 2 plus c. So y equals x squared plus c is the general solution. We don't have initial value, but yeah, those are parabolas, a bunch of parabolas. Okay, next one, when does it equal 0? Well, when y equals 1. So along this horizontal line, y equals 1, you get a bunch of 0 slopes. And undefined, nope. It just depends on y. When y is 0, you get a slope of -1. When y is 2, you get a slope of +1. When y is -1, you get a slope of -2, no matter what x is. And then when y is -2, you get a slope of -3. So a little steeper. Now, what kind of graph does this look like? I'm thinking it kind of looks like an exponential that's been shifted up one, but not a bunch of different other possible shifts. So this might kind of end up like number 2. So if we separate the variables, now remember, it only can be multiplication division. So we have to divide this whole thing over to the left side when we separate the variables. You can't just bring the y over. You can't subtract y because then the dx will get stuck with it too. Okay, only multiplication division. So then we're going to integrate both sides. We natural log the absolute value of y minus 1 equals 1x plus c. We can exponentiate both sides. So we're going to get absolute value of y minus 1 equals e to the x plus c. We can get rid of the absolute values by doing plus or minus. Now I'm going to break this up using rules of exponents. So I'm just going to put a c. E to the c is just some new constant. And then you're going to add 1 to both sides. So you get y equals plus or minus c e to the x plus 1. So sure enough, this is the general solution. It's an exponential, up or down, steeper or less steep. shift it up 1 no matter what. Makes sense with the graph, right? Okay, next one. Where does it equal 0? Well, that would be when the numerator equals 0, right? So when y equals 0, so that's all along the x-axis, so you get 0 slopes. Make them stand out. When is it undefined? So this is the first one of these examples that gives you division by 0. So now technically you shouldn't draw these. They don't exist. But I'm going to draw them because that'll help me kind of see what's going on with the picture. But on the AP test, for sure, don't draw them. Okay? But it's helpful. Now, the other ones, if you plug in 1, 1, you get -1 slope. When you plug in 2, 2, you get -1 slope. Right? -1, -1, you get -1 slope. -1 slope. When you plug in 1, -1, you get a +1 slope. +1 slope. +1 slope. +1 slope. It's kind of interesting. There's like symmetry, like double symmetry here. 1, 2, 1 for x, 2 for y would be a slope of -2, down 2, down 2. 2, 1. So there's a, let's see if we can find any others that are like that. 1, -2 would be a slope of +2. -1, 2 would be a slope of +2. 1, -1, 2. -1, -2 is going to be a slope of -2. Okay, 2, 1. 2 is for x. That's going to be a slope of 1/2. So that's going to be -1/2. Down 1/2. Okay, down 1/2. This one, 2 negatives is going to be slope of 1/2. Up 1/2. And you can start to see the pattern here. If you do one with the wrong positive or negative slope, it should stand out bad. 3, 1 is me -1/3. So down 1/3. I bet this one's going to be up 1/3. This one's going to be up 1/3. This one's going to be down 1/3. And then 3, 2 would be -2/3. Down 2/3. So that's your slope field. Now, what kind of graph does this look like? This looks like a rational function to me with a vertical asymptote, a horizontal asymptote. One is probably this, and the other one's probably the other two, or something like that. So let's see if we can separate the variables. So it's going to be dy over y. I would leave anything other than y's on the right side if possible, like in negatives or numbers. So we've separated the variables. Integrate both sides, plus c, exponentiate. To get rid of this absolute value, you're going to have to do plus or minus. Now, this, using rules of exponents, is the same thing as that. So that's just going to be a new c value. Here, the e and the natural log are going to cancel each other out, but you got to bring the negative in first. You can't cancel them out if there's anything extra outside. So you got to bring it as a negative exponent. So what it's going to look like is c times 1 over the absolute value of x. And that's it. That's your general solution. So it is like a rational function. So it's probably going to be either the two tops or the two bottoms, depending on whether you get a plus or a minus for the c value. So it's like a rational function. Okay, number 7 is kind of like a typical first response problem involving differential equations. I mean, typical for many years. So here's your differential equation. It's just a derivative. Sketch the slope field. They're going to tell you how many points to do it at. And you want to pay attention to that because a lot of times they'll leave dots off here. And they're actually trying to help you because there's going to be certain places where you shouldn't draw them because it's undefined or whatever. There's 12, so make sure you have 12 when you're done, that you didn't miss any, that you didn't do too many of them. I'd look for where does it equal 0, and that's going to be when x equals 0 or y equals 1. So when x equals 0, you're going to get 0 slopes. So you just got 1/3 of them. When y equals 1, you're going to get 0 slopes. So we already got half the points. In typical infer response, they don't give you a ton of points. There's only 12 here. We already did half of them. Is it ever undefined? No. So I think I'm just going to plug these in. There might be some kind of symmetry, vertical or horizontal. When you plug in 1, 2, 1 for x, 2 for y, you get a slope of 1. When you plug in -1, 2, you get the same thing because the negative gets squared. So that's a slope of 1. When you plug in 1, 0, 1 for x, 0 for y, you get a slope of -1. When you plug in -1, 0, you get a slope of -1. When you plug in 1, 3, 1 for x, 3 for y, you get a slope of 2. And -1, 3, you get a slope of 2 also. So that's your slope field. That'd usually be worth like 2 out of the 9 points, 1 for all the 0 slopes and 1 for all the other slopes. You miss one out, you lose that whole point. Okay, part B says, while the slope field in part A is drawn at only 12 points, it is defined at every point in the xy plane. It keeps going. And there's no points where it's undefined. So every point, describe all the points in the xy plane for which the slopes are positive. Now, you could look at this picture to kind of get a rough idea. It looks like they're positive here and here, not here, not here, not here, not here. But really, I wouldn't rely on the picture. The picture should confirm it, but I'm going to use algebraic techniques. So when does it have positive slopes? Well, just take your derivative and make it positive and solve this. Well, when's this going to be positive? Well, it doesn't really matter what x is. X is positive or negative is going to come out positive. So it's really depending on this. Y minus 1 has to be positive, which means y has to be greater than 0. There is one restriction on x. X cannot equal 0 because if it does, then you don't have a positive slope. So these are the two restrictions that have to both be true to get a positive slope. So you could say all points where y is greater than 0 and x doesn't equal 0. So that's one way to describe it. You could describe it more graphically. You could say all points above y equals 1, the horizontal line y equals 1, and not on the y-axis. X equals 0 is the y-axis. And that kind of fits your picture too. So, I mean, the picture makes sense with these, but the picture is kind of hard maybe to get that big. Algebraically, I think that's just better. Now it says find the particular solution. So that means we're going to solve the differential equation, actually find the c value. I'd find it right away. So we're going to separate the variables. So to separate the variables, we need to multiply or divide. So we're going to divide y minus 1 over here. You get x squared dx, multiply the dx by the other side. It's called separating the variables. That's usually worth like a point. Then we're going to integrate both sides. Natural log of the absolute value of y minus 1 equals x cubed over 3 plus c. The antiderivatives are usually worth a point. The plus c is worth a point. Let's find the plus c now. Even though on the solutions I post, I probably didn't do it that way. I waited till the end, which you can do, but I think that's a lot harder. So this is the x, this is the y, so we plug 3 in. So c equals natural log of 2. So we're going to rewrite it. Okay, now we're going to solve for y. So we're going to exponentiate both sides. You can use rules of exponents to break this up because it's all one big exponent. You can't distribute. You can use rules of exponents. So that's going to be a 2. Get rid of the absolute value. It's going to be plus or minus 2e to the x cubed plus 3. Now, since we found the c already, the plus or minus has to be figured out. So I'd figure it out right now. Use the initial condition. If I plug 0 in here, it's going to be e 0, which is 1, times 2 is 2. And I plug a y equals 3 in here. The only way that's going to be true is if I go with positive. So you just got to check it. And then we finish solving. So that's your solution. That's the particular solution, a specific solution. But you also need to state the domain. Now, the domain depends on this, your answer, like, are there any issues with domain, any division by 0, natural logs of negatives or 0, even roots of negatives. Okay, but then you also have to check the derivative and say, are there any issues where it would be undefined? So you go back up here and you say, okay, any division by 0, logs of negatives or 0, even roots of negatives. So no issues there, no issues there. The domain is all reals, but usually asked to write it as like an interval, single open interval. You write it like that. I mean, this is also the same thing as all real numbers, but I think on these kind of problems you should write it as an interval notation. But you gotta start paying attention to that. That's one of the things that people forget to do, or even if they remember to do it, they mess it up. Okay. Now for an interesting problem on the back. Predator prey. Okay. So the figure shows a slope field for a differential equation that represents the relative populations of deer D and coyote C that prey on the deer. The slope at any point represents this. So this is a differential equation for coyotes to deer. Okay, coyotes on the vertical axis, deer on the horizontal axis. Okay, so at the point, it looks very circular, right? At point 80, 20, so here's 80, here's 20. At point 80, 20, there are, you might go ahead and label this real quick. 80, 20, there are relatively few coyotes, 20 coyotes to 80 deer. Would you expect the deer population to be increasing or decreasing at the point? Which way then would the graph of the solution start under this condition? So the graph, the solution, the particular solution is like it's kind of like this circle, oval, right? That's the particular solution. Which direction, though, are they asking is it going? So, just common sense. There are more coyotes than deer. So the deer have lots of food, and the coyotes have lots of food available. The deer, on the other hand, have less resources because there's so many of them. So they're not going to necessarily be, so the coyotes, I think, are going to be, there's going to be gaining more coyotes. So the direction is going to be this direction. More coyotes and more deer, but the deer population is slowing down. Okay, but the coyote population is increasing. So I would say coyote population is increasing. It says which would you expect the deer population? Okay, so the deer population is increasing because there are less coyotes to eat them, but at the same time, the coyote population is increasing because they have more food. So I'd say counterclockwise. All right. Sketch the graph of the solution to the differential equation. Subject to initial condition 80-20. Describe what is expected to happen to the two populations under this condition. So I already sketched it. Okay. And we were already talking about it. I'm going to say the deer population increases and the coyote population increases. at first. Until, what point is this? That kind of looks like 90, 35. Until 9035, then the deer population decreases as coyotes continue to increase. And that could be, a couple problems. Coyotes are increasing, so there's more predators, so that could start to affect the deer population. Also, the more deer there are, the less resources for the deer population. Okay, number 3. Suppose that the initial number of deer is increased to 120 with the same 20 coyotes. Sketch the graph. What unfortunate result is predicted? Okay, so we're starting at 120, 20, which is like right here. And so we could sketch the particular solution. It should follow the slope field and not go against any of the slopes. Okay. And it's going to be the same direction. So that's our sketch for 120, 20. Okay. So what's the unfortunate thing? Well, we're going along, deer increasing, coyote increasing, deer are decreasing, coyote are decreasing, deer are decreasing, coyotes start to increase, but deer are still just decreasing until there are no more deer. Or until there's no more coyotes. So I could say eventually the coyote population goes to 0. Negative, right? There's no come back. When the let's see, I don't even know. When the deer, wait, did I do the right one? Yeah, I think so. When the okay, eventually the coyote population goes 0 when the deer population ends at 30. Then I guess deer would increase until there's just too many deer. But okay, suppose that the initial deer population had been 140 with the same 20 coyotes. Sketch the graph. What unfortunate thing. Okay, so we're going to go to 140, 0 right here, 140, 20. And something else happens. Okay, directions, same direction. Okay, so it says eventually the deer population goes to 0. When the coyote population ends at 50, which isn't good for the coyotes because they depend on the deer. So we just killed off their food supply. At 135, what seems to be happening in two populations? What seems to be happening at 0.65, 80. So 135 was like right here. And it looks like deer have stopped increasing their churning point, and coyote population are on like a super fast growth rate or their biggest growth rate, maybe we could say. So 135 deer population is at its maximum, right? It's maximum deer population, maximum, and will begin to decrease as the coyote population is increasing the most. So max derivative, max rate of change at 6580. Let's look, 6580. So 10, 20, 30, 40, 50, 65, 80. So it's kind of a similar thing, but now the coyote population is at its max population, and the deer are decreasing the most, which kind of makes sense when there's the most coyotes. Coyote population is at its maximum and will begin to decrease as the deer population is decreasing the most. All right. Okay. 6. Does there seem to be an equilibrium condition for which neither population changes? Is there one place where everyone just stays the same all the time? Right here. Right? 65, 35. Say 65, 35. Population does not change. What did you learn as a result of doing this exploration that you did not know before? I'll let you fill that in. That's for you. I learned that it's the circle of life. I don't know the rest of the words, but I can see little baby Lion King being held. All right. Here's a few problems out of your book. So we try those right now. Some good problems. Challenging your understanding of slope fields. So, this is on page 328, number 49, 50, 61, 62. So these are all multiple choice, but you should probably write some stuff down. 49, I'm going to draw a picture. 49, they give you dy dx equals 1 over 1 plus x squared, and y0 equals pi over 2. So this is a differential equation with initial condition. We could potentially solve for it, but this is multiple choice, so let's see if we can take advantage of some things. So they gave us some graphs here. I'm just going to sketch these real quick. So that's A. That's B. C. Trying to sketch this right. And a lot of these have pi over 2 on them because that's the initial condition, which well, so I think that's it, A, B, and C. So it says, so explain how you eliminated two of the possibilities. So we're trying to, A, determine which graph shows the solution of the initial value problem without actually solving the problem, which is good. That's less work. So what are some things to look for here? One of the things I've been telling you is to look for like a zero slope, right? I mean, that's something I would do. This initial condition pi over 2, that doesn't really make sense on any of these, really. That's not something that needs to be true because that's on the original graph. These are graphs. Okay, no, these are graphs of the solution. So that should be true on all of these, which it is. So that doesn't help us. Zero slopes. Is this slope ever zero? No. So since this one has a zero slope, I would throw it out just for that. How about undefined? Nope. Okay, that doesn't help. How about positive and negative slopes? When is this slope positive? When is this slope positive, greater than zero? All x's, right? Every x. No matter what you plug in x, this is always going to be positive. Always positive. So any graph that has negative slopes, throw out. This one also had negative slopes. Throw it out. So just by process of elimination, this is the only one that could be it so far. Time's running out. Okay. 50 is multiple choice, same idea. So this is good because you could get multiple choice like this on your next test and not want to do all the work. Maybe you can't. Maybe I give you something that can't even be solved. Can't be solved using our methods. So this one was, well, I'll write down the problem in a second. Okay, so the differential equation was dy dx equals negative x and y negative 1 equals 1. So they got to have y and negative 1, 1, which they all do. So that doesn't help you eliminate anything. Now this, when is it equal to 0? Well, that'd be when x equals 0, which this one does, this one does, this one doesn't. So you can eliminate a just from that. They're not undefined. You could say, okay, when x is positive, the slope is negative. When x is negative, the slope is positive. So we're looking for one that is negative on the right, positive on the left. Negative on the right, positive on the left. Negative on the right, positive on the left. This one's just negative all the time. So negative on the left, positive on the right. So the only one that, based off that could be it would have to be B. So that this is just good strategy. So you have to, do all the work. Okay, 61 says a slope field for the differential equation will show what? So dy dx equals 42 minus y. Slope field will show. So what's it going to show? It's an initial condition. Says a line with a slope of negative 1. And a y-intercept of 42. Now, there, A is trying to trick you into thinking this is y, so A is out. I mean, and we could start to solve it. I mean, I don't know if these are the problems that said they couldn't, that you shouldn't. Let's see, it'd be dy over 42 minus y equals dx. So it'd be natural log the absolute value of 42 minus y. You would need an extra negative. Okay, so then You get exponentiate. It's going to be some kind of exponential, right? So what did B say? B says a vertical asymptote at 42. At what? At x equals 42. No. A horizontal asymptote. Well, if you were to keep solving this, exponentials have horizontal asymptotes, right? So this one has a horizontal asymptote at 42. And that's what they're saying at y equals 42, positive 42 as a horizontal asymptote. So the answer is C. You could just check D and E. D says family parabolas, no. E says family parabolas opening left, no. It's family exponentials. Okay, 62 says, for which of the following differential equations will the slope field show nothing but negative slopes in the fourth quadrant? Negative slopes, fourth quadrant. Now, it doesn't say it can't be negative other places, but it says only negative slopes in the fourth quadrant. So A is dy dx equals negative x over y. Now, the fourth quadrant, x is, this is the fourth quadrant. X is positive, y is negative, right? So if you put positive x's, negative y's, this is going to equal positive no matter what. So that one's out. B, dy dx equals xy plus 5. Well, this is always going to be negative, right? For sure, in the fourth quadrant. But then you get added 5, so it just depends. Sometimes it's negative, sometimes it's positive. If this result is smaller than 5, then you're going to get positives, right? So that one's out. C, dy dx equals xy squared minus 2. So here, y is always going to be negative, squared is positive, positive. So this is going to be positive probably most of the time and negative sometimes when this result is smaller than 2. D, x cubed over y squared. Well, x is positive, so that's going to be positive. Y is negative, it's going to be positive. This is going to be positive for sure all the time. So that one's out. And then this one, y is going to be negative, x is positive, squared is still negative. This is for sure always negative. And then we're subtracting, so this is for sure always going to be negative. That's the one. So you can narrow these down without sketching all these slope fields and stuff. You can find the answers. All right, that's it.